All right, good morning, everybody. It is early. It's 7:25 on a Friday morning before the Christmas exams, and we had a request to hear about static and translational equilibrium. So here we go. Remember to check your definitions and know those. Static equilibrium, okay, occurs when all the forces acting on an object cancel out and the object's not moving. Okay. And I have a very exciting picture of a rock here, which is in static equilibrium because you have two forces acting on the rock. Gravity's pushing down, and the force of the normal is pushing up, and so the rock doesn't move. It's balanced. It's in static equilibrium. I'm not sure that I'd be rushing to stand under it right now, but right now you're safe. It's there. Okay, translational equilibrium occurs when all the forces, equilibrium in general is all the forces adding up to zero, okay, and translational equilibrium occurs when you're moving and all the forces add up to zero. And so if you're moving and the forces add up to zero, you keep moving in the same velocity. Okay, it's that whole Newton's first law, an object in motion staying in motion unless an outside force acts on it. So I found this video of somebody's first parachute jump with cheesy music, and as they jump out, here he goes. Okay, gravity pushes them down, and as they move faster and faster and faster, the air resistance increases, and it'll increase until the point where the air resistance equals the force of gravity. And you see, well, that's what happened right there. They didn't slow down, okay, but their acceleration decreased, and so now air resistance is pushing up at the same rate that gravity is pushing down, and they're in what's known as translational equilibrium. Okay, all the forces acting on them add up to zero. And soon, are they going to pull the chute on him? Soon they're going to increase his air resistance, maybe. And when they do that, they increase his air resistance, then he's going to slow down until a new translational equilibrium is established. Watch, there he goes. And they're not going to put the camera up. Oh well, that's so it goes. Okay, so to give you a visual of this, okay, if we take a look at vector addition, your old buddy, the simulations. You guys love simulations. Well, no, you don't, but that's fine. Let's say I put an object here, and I put this red force acting on it here, like that. And I put another force, and I'm going to act on it this way, like this. Okay. So force number one goes up to the right, force number two goes up and to the left. Force number one moves 1, 2, 3 units right and 1, 2, 3 units up. And force number two goes 1, 2, 3 units left, and you know what, let's change it, let's do this. Let's go 4 just to keep it interesting. 4 units left, 1, 2, 3, 4, and 2 up. Alright, so just realized I need more space. So if I need to have this equal static equilibrium, okay, if I put a vector sum in there right now, okay, this shows this vector plus this vector, and you can see there is a sum there. Alright, if I need something to be in static equilibrium, well, let's see, right now I have 3 units of force to the right and 4 units of force to the left. So my third vector that I'm going to add has to have one more force unit to the right. Okay, it has to. And if I do that, I'll have 1, 2, 3, 4 units to the left. Just notice that was off center. 1, 2, 3, plus another one, 4 units to the right. So the object doesn't have any forces acting to the left or right. It's in equilibrium in the left or right direction. Going up and down, we have 1, 2, 3 units up, 1, 2 units up, so 5 units up. And so to be in static equilibrium, I need to go 5 units down. Alright, so what I've done is I've added a third vector that goes 1 unit to the right and 5 units down. And if I say show sum, there isn't any sum to show. It's in static equilibrium or translational equilibrium. Okay. A quick problem to illustrate this. Find the tension. Here, I'm going to go through this one step at a time. There we go. Find the tension of each rope below. Okay, and we've done a few of these now. This This is a system that has 3 ropes, T1, T2, and T3, and a 25 kilogram mass hanging from it. Alright, well T3 is pretty easy. T3 is just the weight of that 25 kilogram mass, and that's equal to 25 times 9.81 is 245 newtons. So T3 we've already solved. Okay, the force going down through T3, tension 3, is 245 newtons. Now, we're going to use that information, that 245, we're going to use that to look at T1. Alright, if you consider T1, here it is here, there's a 40-degree angle, and here I've redrawn it. Okay? T3 pulls down with 245 newtons. And this system is in static equilibrium, which means that T1, which pulls to the right and pulls up, has to pull up with those same 245 newtons. If it doesn't, then you aren't in equilibrium. Your forces don't add up to 0. Okay, so what I've done here is I've drawn T1 with its components, T1x moving to the right and T1y moving up. And I've said that T1y has to equal 245 newtons to cancel out T3. Okay, so then I do a little trigonometry, which you guys are getting really good at. Sine 40 equals opposite over hypotenuse. Sine 40 equals 245 over T1, and I get T1 equals 381 newtons. Alright, so now going back up, we know that this is 381, and we know this, T1 is 381, and we know T3 is 245. We need to solve for T2. We need to know how much force it pulls to the left. Alright, the system is in equilibrium, so T1 pulling to the right has to pull to the right with the same force that T2 pulls to the left. So if I put the revealer on again, okay, we're going to solve for T2 this time, and we have a few choices. Alright, T1x, we said, pulls to the right and it pulls up. And it pulls to the right with the same force as T2. So we have choices now because we know our hypotenuse and we know our opposite. We can use Pythagoras or we can use trig to solve for it. And I chose trig. Okay, well, you can use any one you want. Alright, I said that the tangent of 40 equals the opposite, which is 245, over the adjacent, which is T1x. And I solved for T1x and I got 292. And what I didn't do is, I'm not sure that I'll be able to do this, T1x pulls to the right with the same force that T1x pulls to the right with the same force that T2 pulls to the left. And so therefore, I didn't write my last statement, T2 equals 292. Hope it helps. Hope the studying is going well, and we'll talk to you again soon. Any requests, keep them coming, and I'll do my best to post them up.